Okay guys, here's lesson 3, distributing binomials. So I've used the term polynomial a few times, and I've defined it also. It's an expression where all the powers are whole numbers. So whole number power, whole number power. This has a power of 1, which is a whole number. If you have something like a square root of x, or x in the bottom of a fraction, or x with a non-whole number power, you don't have a polynomial. So all of our polynomials we're dealing with in this chapter are going to be having whole number powers at all times. We can describe polynomials a couple ways. One is by the number of terms. Okay? If a polynomial has one term, we call it a monomial, because mono means one. So like this is a monomial, here's a monomial, here's a monomial. 2 terms is a binomial, because bi means 2. 3 terms is a trinomial, because tri means 3. And 4 terms, we don't say quadnomial that often, but you can. You can also just say four-nomial. But 4 terms is a quadnomial. So here's a 4-termed expression, here's a 3-termed expression, here's a couple 2-termed expressions. Monomial, binomial, trinomial. Makes it easier for us to discuss what we're talking about with these types of terms. But, you know, once we get above 4, I've never heard the term pentanomial, hexanomial, sexanomial, octanomial, nonanomial, right? Like, we have words that are, I think, Greek in origin that mean 0, 1, 2, 3, 4, 5, 6. But we just say 5-nomial, 6-nomial, etc. Okay, so if you had a 6-termed expression, I would literally just call it a 6-termed expression. I wouldn't even say 6-nomial. I would just say there's a 6-termed expression. But monomial, binomial, and trinomial in particular are ones we have to be aware of and on top of. We can also describe them by their biggest power. Remember, biggest power means degree. Okay, the degree is the biggest power. If the biggest power is a 0, we call it a constant. So like the numbers 16, 12, 0, -4. Those are all constants. If the biggest power is 1, we call it linear. 2x, -3x plus 4, 1/2 x plus 6. Those are linear because if you have the equation like y equals 2x plus 6, it's going to graph as a line. If you have a degree of 2, if the biggest power is 2, you have a quadratic. If the biggest power is 3, you've got a cubic. And then again, 4, quartic, you don't hear that often, but you can. Other than that, we just call them 5th degree, 6th degree, and 7th degree polynomials. So this can be described, like I can take terms like this and describe them very specifically. This would be called a quadratic trinomial. Quadratic because the biggest power is 2. Trinomial because there's 3 terms. This would be called a cubic binomial. Cubic because the biggest power is 3. Binomial because there's 2 terms. And this would be called a linear monomial. Linear because the biggest power is 1, and monomial because there's just 1 term. So we can discuss these types of polynomials very specifically, and that's very helpful. What we're going to do today is we're going to be multiplying binomials, and they're going to result in quadratic trinomials. Mostly. Every once in a while we'll get a binomial, but for the most part we're going to multiply to get quadratic trinomials. That means they're going to multiply into these quadratics that we've seen before. Ax squared plus bx plus c. So right now, all of these expressions, I'm going to do a lot of examples, all of these expressions are coming to us in factored form. I'm going to put them into standard form. Now the first couple I'll do very slowly, and I'll start getting faster. And if you need to slow me down by pressing pause or going at half speed or something, you can. When you're multiplying binomials, each individual term in this parenthesis is going to multiply to each term in this parenthesis. So this x is going to multiply with this x to become x squared, and it's going to multiply with this -6 to become -6x. This 4 multiplies with this x, and this 4 with this -6. Then I combine my like terms, and I match them up in that way so the like terms are right on top of each other. -6x plus 4x is just -2x, and I've multiplied. I've done the distribution, multiplying everything from one parenthesis into everything in the other. That's the process. It's pretty straightforward. 2x times x, 2x squared. 2x times -9, -18x. -3 times x is -3x, and -3 times -9 is +27. Combine my like terms, and I get 2x squared minus 21x plus 27. Boom. So I am now in standard form. I'm converting from factored form to standard form. Hopefully you can get to the point where you can do this without the rainbow. I'll keep drawing the rainbow. You know, x times x is x squared, x times 4 is 4x, 6 times x is 6x, and 6 times 4 is 24. Add these up and put them together, and you get x squared plus 10x plus 24. But maybe you can get to the point where you don't have to be drawing the lines, and you don't have to stack them on top of each other. Like, the dream is that you can do this really, really quickly and really, really accurately. And to do that, you might just see, you know, I'm gonna touch these to show them, but 4x times x is 4x squared. 4x times negative 10 is negative 40. 3 times x is 3x. 3 times negative 10 is negative 30. This was 40x, not 40. 4x times negative 10 is negative 40x. Combine your like terms, you get 4x squared minus 37x minus 30. So I don't care how you do your multiplying, provided you do it correctly. I would like you to be able to do it quickly and correctly. That'd be ideal, quickly and correctly. But correct is far more important than quick. All right, let me talk about how some math books like to show this. And I think it's a little bit silly, but can be helpful. You'll often hear the term FOIL. And I think I've even done this in a video. FOIL means you're doing the first, then the outer, then the inner, and the last. So first, multiply the first term here and the first term here. Outer, multiply the term on the outside and the term on the outside. Inner, think about the two inner terms and multiply them. Last, take the last term from the first parenthesis and the last term from the second parenthesis and multiply them. Then you combine your like terms. Bang, and you foiled. That's a fine way to multiply. It doesn't actually do anything different from what we did when we were drawing rainbows. Okay, it's just make sure everything from one parenthesis goes to the next. So I'll do this last one. If you want to pause it before me and do it in advance, or at least just try to be a step ahead of me as I'm doing it, that'd be great. X times x is x squared. X times negative 3 is negative 3x. 2 times x is 2x, and 2 times negative 3 is negative 6. Combine my like terms in the middle. It's x squared minus x minus 6. All right, so I'm good to my word. I started pretty slowly. By the end, I was going pretty fast. My hope is that with you, after a lot of practice, you might start slowly, but by the end, you can just knock these out real fast because it's important to be able to do these quickly and accurately. Eventually, we see some patterns, though. Okay, so watch what happens with these few problems that I have set up. This is really, really convenient. X times x becomes x squared. X times negative 4 becomes negative 4x. 4 times x becomes positive 4x, and 4 times negative 4 becomes negative 16. When I combine my like terms, negative 4x plus 4x is just 0. Those two things undo each other. I end up with x squared minus 16. This is actually a quadratic binomial, not a quadratic trinomial, because there's only two terms. It's going to happen again over here. Watch. X squared minus 6x plus 6x minus 36 is x squared minus 36. And it's going to happen one more time. What fun. X squared plus 3x minus 3x minus 9 becomes x squared minus 9. Now look at these three problems and see what they have in common. I hope it's pretty glaring, pretty straightforward. Each of them has a plus or a minus of the same thing over here. X plus 4x minus 4, x plus 6x minus 6, x minus 3x plus 3. They always came out into these. And notice how with every single one of these terms, each piece is a perfect square. 16, 9, 36, x squared. They're all perfect squares, and they always have a minus in between. Subtract, subtract, subtract. We call this a difference of squares. This is the word difference. Take my word for it. It's called a difference of squares because that's a perfect square that subtracts, and that's a perfect square that subtracts. It has a formula. It actually has its own pattern that's so common that it has its own formula. If you have a plus b times a minus b, that's going to become a squared minus b squared. Boom. It's that simple. So for some quick examples, if I have x plus 5 times x minus 5, I just know right away that'll become x squared minus 25. If I have x minus 9 and x plus 9, I know right away that'll become x squared minus 81. If I have x minus 10 times x plus 10, automatically I know I'm getting x squared minus 100. It's a difference of squares. So you should be looking for this pattern. I call it a shortcut pretty often. If you have a plus b times a minus b, you end up with a squared minus b squared. It's really great. The next two also have their own patterns. They're similar, but it's not quite as quick or simple, but still quite useful. Watch what happens here. This is x plus 4 times x plus 4. This becomes x squared plus 4x plus 4x plus 16, which is x squared plus 8x plus 16. I'll do a couple more and see if you can see what the pattern is. X squared plus 6x plus 6x plus 36. Put that together, you get x squared plus 12x plus 36. X squared minus 5x minus 5x plus 25 becomes x squared minus 10x plus 25. Okay, now all three of these had the same sort of start. They started, like if you look at x plus 4 times x plus 4, this right here is actually the same as x plus 4 squared. X plus 4 times x plus 4 means x plus 4 squared. Because to square something means you multiply it by itself. So if you square x plus 4, you multiply it by itself. So here's something really, really important. Something that students get wrong all the time throughout their algebra careers. X plus 4 squared is not x squared plus 16. Students frequently just want to square this and call it a day. Sadly, it's not that simple. X plus 4 squared is x squared plus 8x plus 16. And x plus 6 squared is not x squared plus 36. It's x squared plus 12x plus 36. So let me jump down to some clean space. If I have something being squared, I'll do 3, x plus 3 squared. You want to write this out as x plus 3 times x plus 3, and then just do the foiling. X squared plus 3x plus 3x plus 9. Put your like terms together, x squared plus 6x plus 9, and you got it. So here's the shortcut. If you have something being squared, the first term is always a squared, and the last term is always b squared, but the middle term is 2 times a times b. So let me try to make sense of that for you. Say that I had x plus 10 squared. Well, I'm going to call my x value a and my value of 10 b. So the first term I'm going to get, which is going to be a squared, is just x squared. X times x is x squared. The last term I'm going to get, which is b squared, is going to be 100, because 10 squared is 100. But the middle term is 2 times a times b, which is 2 times x times 10 So it's x squared plus 20x plus 100. This shortcut might not be so worth trying to memorize or hang on to. It's not near as fast as the difference of squares. But you need to understand a plus b squared is not a squared plus b squared. You cannot be somebody that keeps writing that or doing that. We'll talk about it a ton in this class. I think that's good for today. That was distribution. See you next time.